Hey everyone, welcome back to the channel. I'm Vaibhav, and here's a question that might have puzzled you. Why do two cars of the same age sell for very different prices? This is exactly the limitation we hit with simple linear regression. And today, we're going to solve this puzzle using multiple linear regression. But first, let's establish some important terminology that you'll encounter throughout machine learning. If you're learning data science and finding this series helpful, please subscribe to support more technical content like this. Before we dive into our car example, let's clarify the key terms we'll be using. In machine learning, we have different names for the same concepts depending on the context. The variable we're trying to predict, car price in our case, has several names. We call it the dependent variable, the target variable, or simply the target. It depends on other factors, hence dependent. The variables we use to make predictions have their own terminology. We call them independent variables, input variables, features, or predictors. These are independent because they influence the target but aren't influenced by it. So, in our car example, price is our dependent variable or target. Age, mileage, and brand are our independent variables or features. You'll also hear the term feature engineering. This means creating or selecting the right input variables for your model. It's a crucial skill in machine learning. Now let's see why understanding multiple features matters. In our previous videos, we used simple linear regression with just car age to predict price. But let's see what happens when we apply this to real market data. Watch this animation showing our familiar age versus price relationship. You can see our downward sloping line, but notice something critical here. Look at these two cars in the animation. Both are 4 years old, but one sold for $22,000 while another sold for only $16,000. Our simple model predicts both should cost $19,000. This $6,000 variance tells us that age alone is insufficient. We need additional variables to explain these price differences. This is where multiple linear regression becomes essential. Instead of one feature, we use multiple features simultaneously to make predictions. Let's add mileage as our second variable. Watch as our visualization transforms from 2 dimensions to 3 dimensions. In this 3D space, you see 3 axes: car age, mileage, and price. Our data points are now scattered throughout this cube. Those two 4-year-old cars, one has 30,000 kilometers, the other has 80,000 kilometers. This explains their price difference. Multiple regression fits a plane through this 3D space instead of a line. The algorithm finds the plane that minimizes prediction errors across all dimensions. Our equation becomes price equals intercept plus age coefficient times age plus mileage coefficient times mileage. The model determines each year reduces price by $1,800 and each 1,000 kilometers reduces it by $50. So our low mileage 4-year-old car prediction comes out to about $20,700. The high mileage version, approximately $17,800, much more accurate than our simple model's single $19,000 prediction. Now let's add car brand as our third variable. Here you can see how we handle categorical data like Toyota, Honda, or BMW. We use dummy variables. Each brand becomes either 0 or 1 in our equation. This creates separate intercepts for different brands. The visualization is now 4-dimensional: age, mileage, brand, and price. As you can see, it's becoming impossible to visualize clearly. This brings us to a crucial limitation. While I can show you 3 dimensions in these animations, real-world models often use dozens or hundreds of features simultaneously. Think about what else affects car prices: engine size, fuel efficiency, safety ratings, market demand, location, and many other factors. Each could improve our predictions. But here's where we must transition from visual understanding to mathematical optimization. Beyond 3 dimensions, we rely on algorithms rather than intuition. Now that we see models can handle many variables, let's talk about the challenges that come with adding too many. First challenge: feature selection. Adding irrelevant features can decrease performance through overfitting. More isn't always better. Second challenge: multicollinearity. When features are highly correlated, like engine size and fuel consumption, coefficients become unreliable. Third challenge: the curse of dimensionality. More features require exponentially more data to maintain statistical significance. From a business perspective, this creates important trade-offs. Simple regression is fast, interpretable, and needs less data, but may be insufficiently accurate. Multiple regression can be highly accurate, but risks overfitting and becomes harder to interpret. The key is matching model complexity to your specific problem. and available data. Simple regression works well for straightforward relationships like advertising spend versus sales. Multiple regression is necessary for complex phenomena like customer lifetime value or market price predictions. The decision framework is: do you need high interpretability or high accuracy? How much data do you have? How many relevant features exist? In our next video, we'll explore how to measure which approach actually works better. We'll cover evaluation metrics, validation techniques, and how to detect when you're overfitting your model. We'll also see how to avoid common mistakes beginners make when testing models. If this explanation of simple versus multiple regression clarified the concepts, subscribe to the channel. Your support enables more technical deep dives like this. Comment below, what's one business problem you encountered that would need multiple variables rather than just one? I'm curious about the complexity you're dealing with. Thanks for watching, and I'll see you in the next video where we tackle model evaluation and validation.